Alrighty, now you may have noticed my screen switched randomly. Apologize about that. This is the second page of your packet, so go ahead and turn over to the second page now. This page starts out with section 0.01, exponent rules. Cool. Okay, so we're going to start with exponent rules today. But let's talk about what exactly is an exponent. So let's jump down to below the vocab box here. We will recall that an exponential expression, one of our objectives is to figure out what that is. So our exponential expression means an expression that contains an exponent, right? So we've seen these before. They're definitely nothing new. They just now have some fancy name to them. For example, 2 to the 5th is an exponential expression. 2 to the 5th, right? It's got an exponent in it. It's got the other part, right? And let's talk about that other part. So 2 to the 5th, the 2 is what we call the base, the number that is being multiplied over and over again. And then the 5 is the exponent. So then how many times something is being repeated. So in other words, 2 to the 5th means 2 multiplied by itself 5 times. 5 times. And then if we actually compute that out, we get 32. So 2 to the 5th would be 32. But the exponential expression part would be 2 to the 5th. Let's see if we can come up with some other exponential expressions that are given to us in English, and we need to convert it to a mathematical statement. So how would we write 2 to the 4th? Now often in these videos I'm going to ask you to pause, and I'm going to ask you guys to talk about it yourself. Okay, so I would like you to do that. And if you don't, if you choose to just sit there and kind of drool off and play with your fidget spinners or whatever, that's going to be really, really painful for you down the road when you can't remember any of this and you've got homework to do or you've got a test to take and all of a sudden your grade goes in the toilet. So I strongly recommend every time I say try this yourself, you actually try it yourself. Alright, so go ahead and pause now. And if you want to, you can talk about all 3 of these. But we're going to start with 2 to the 4th. Alrighty, so I hope you had a chance to pause. 2 to the 4th looks like this. 2 would be the base, and then 2 the 4th would look like something like that. And then it does ask us to simplify. So we'll simplify 2 to the 4th means 2 times 2 times 2 times 2, right? Or 2 times 2 is 4, times 2 again is 8, times 2 again is 16. So 2 to the 4th is 16. All right, let's try another one. The number 6 multiplied 3 times. The number 6 multiplied 3 times. So in this one, it tells us that there is a number 6 being multiplied by itself 3 times. And that sounds like 6 is the base, and then 3 times tells us the exponent. Or in other words, 6 times itself 3 times, right? Or 6 times 6 is 36. 36 times 6 is 216. I do believe. Yes, 216. Fabulous. Let's do one more. 16 cubed. You'll see this number a lot. Sometimes if you don't want to say twice or 3 times or something like that, we come up with a special name. This one is cubed, which means 3 times. So 16 is still our base. That was usually, it looks like they're usually telling us what to square or what to take something to the power first, right? So our base is usually listed first. Not always, but sometimes, or but most of the time. So 16 will be our base. And then it's cubed, and think cube has 3 dimensions, right? Cube has a 3-dimensional object, so that's the same thing as times itself 3 times, or 2 to the 3rd power. So 16 times 16 times 16, that's what that means. We could do that. 16 times 16, it's going to be 256 times another 16. That's going to be 4,096. You may be hearing the little clicks of my calculator in the background. That's fine, right? If you don't want to by hand multiply 16 by 16, that's okay. But if you are trying to multiply 2 times 2 times 2 times 2 and you can't do 2 times 2, then I definitely recommend putting the calculator away so that you can practice that, right? 16 is a little big of a number, I get that. But something down here you should probably be able to do by now. Alrighty, so that's exponential expressions, setting those bad boys up. Looking good. If you have any questions at all, you can pause the video here, because from here we're going to talk about how to combine them. And if you are having issues with what a base is, what an exponent is, then you need to talk about it now because it only gets more complicated from here. Alrighty, so exponent rules. Exponent rules, there are 6 of them. First one is called the product rule. Then you have the zero exponent rule. I'm just going down this little chart here. Negative exponent rule, quotient rule, power over power rule, and distribution rule. There are 6 of them. Chances are you've actually probably seen these before. We are not going to read this entire table because I am fully aware that you guys are in 9th grade now, and you can read, hopefully. If, however, when you're doing homework and you forget, what is the product rule? I totally forgot. Okay, hold on, let me see. That is when to use. Two bases of the same kind are being multiplied together, I add the exponents. Oh, okay, cool. So that's what this is for, right? Just be wary on this last row here. This is what not to do, okay? These are common mistakes that people make. So don't think that that's the row you want to look at when you're applying it. You want to look at over here on how to use, okay? And there's an example of how to actually do it, not the bad example, okay? Alrighty. But in order for us to, have a little more fun today, we're not going to just sit here and read the chart. We're actually going to try out a few of these on our own. So let's go down to 1.1. Use the product rule to simplify the expressions. Alrighty. I've got these two expressions here. I've got 3 to the 4th. And 3 to the 7th. We're going to use something called the product rule. Now, a product, if you recall, is a multiplication, right? That's what that is. A product is a multiplication. So, this rule only applies when things are being multiplied. If they're not being multiplied, you cannot use this rule, okay? There's another thing that has to happen. You have to be multiplying by the same base. I'm wondering where... Sorry, I'm not really sure where my eraser went. One sec. There we go. Okay, fine. So we have to be multiplying by the same base. Now let's recall, what is a base? Well, the base is the number that is being squared or cubed or to the 4th, right? So in this case, the 3. These guys both have a 3, so the product rule does apply here. If this was a 4 to the 4th and a 3 to the 7th, the product will not apply here. So we need to have the same base. We'll write it down somewhere else. Why is this happening? Okay, so the same base, we can write it over here. Same base. And they must be multiplied. Alright, otherwise this doesn't work. Otherwise the idea doesn't work. Now let's talk about this. Okay, so it seems like we've got the situation here. Now in the chart it just says to add the exponents, but let's think about why. Let's think about why. In this first expression here, this 3 to the 4th, well, what does that mean, right? We just did a whole bunch of examples of what that means. That means 3 times itself 4 times, right? 3 times 3 times 3 times 3. Then we have that being multiplied by a 3 to the 7th, which is, let's use a color we can actually see. Let's use orange. 7 more 3s. So 3 times 3 times 3 times 3 times 3 times 3 times 3. Now if we take a look at this, well, we've got 4 3s times 7 3s, right? And it's all being multiplied. Even though it's in different colors, the same thing's happening over and over and over again. You've got 3 multiplied by itself. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. Or in other words, 3 multiplied 11 times, 3 to the 11th. 3 to the 11th. Sorry, I'm going to erase that because that looks horrible. Okay, much better. We'll do it in green. 3 to the 11th. Now, if we look closely, so that makes sense, right? We had 11 3s, we squish them all together to get 3 to the 11th. If we go back up here to the problem itself, well, the product rule says when you have the same base and they're being multiplied, you add the exponents. So let's try that. If I add this, I get 3 to the 4 plus 7, 3 to the 4 plus 7, or also 3 to the 11th. So I can take a shortcut. I don't have to sit there writing out 11 3s. I can just add those exponents because that's essentially what we're doing. We're combining the exponents through addition. Alright, so let's try another one. Just kind of hammer it home. Here we've got 5 to the 3rd times 5. Now what is the exponent on that second 5 there? There is an exponent. Be careful. Alright, I hope you said it was 1. 5 to the third times 5 to the first. Remember, if there's no exponent, we just mean a 1. It's kind of like multiplying by a 1. It's not going to change anything, right? 5 times itself one time is just 5. So we've got an exponent of 1 here. So we can apply that same product rule, but we can also think about it this way as well. We've got 5 times 5 times 5 times another 5. It looks like we should get 5 to the 4th. And then if we go up and add the exponents, 5 to the 3 plus 1, we do again get 5 to the 4th. These guys match. So it looks like the product rule works no matter what. So we can just, from here on out, we can just add those exponents. Remember, at any point if you're confused, you need to stop the video and talk and ask questions. All right, let's try the next one. The next one's slightly different, right? It's got 3 of them, right? But remember, product, always the same thing, no matter how many times over and over and over again. You just pick whichever ones you want first. That's called the associative property. So I could do these two guys first, or, this is getting annoying. That's okay. Or we could do the second two guys first, and then we do the third one after that. It doesn't really matter which ones you do first. I think I'm going to start with the first two, just because it's a little easier to see. Whoops. That's okay. So I'm going to start by combining these guys. And another thing different about this problem is that it's a variable, but remember, variables are just numbers we don't know yet. So as long as they match, as long as they're both y's, then you've still got product rule, right? It didn't say anything down here about them having the same number base. It didn't say that they had to be the same number. They just have to be the same, right? So it's y. So maybe we don't know this y, but whenever we do find it out, we can plug it in. It's going to be the same, right? So it turns out y is 2. Then you've got 2 to the third, 2 to the 8th. But right now, we'll just keep it as y, and we can combine them the same way. So we'll start with what's in the purple here. Product rule says I have same base, and they're being multiplied. So I can add the exponent. I end up getting y to the 3 plus 8, or y to the 11th. And then that's still times y squared. I can do one more time from here, and I end up getting y. Just kidding. Sorry. I end up getting y to the 11 plus 2, or y to the 13th. And that would be my final combination. So again, it's variables, nothing changes, ever. I mean, that's a general fact. Variables have to follow every single rule that a number does. They have to follow a few more because you don't know anything about them, but they're really not that special. Like, they think they're all that, but they're really not all that. Like, they're pretty much just numbers we don't know. Like, they have to follow all the same rules. So chances are, if you can do something for a number, you can do it for an exponent. Now, that's that's like 99% of the cases. Obviously, there's a few that are sort of an issue, but basically, variables aren't that special. All right, let's talk about one more. We've got this situation over here. Now we've got two terms being multiplied to each other, and we'll talk again about what a term is, but remember, that's a lot of different stuff. That's, well, yeah, we'll talk about what a term is, but these are basically terms. We've got two different ones here, and remember that not only can we multiply in any order, right, we can start with any two we want, that's associative property. There's something called the commutative property, which means we can switch things around any way we want to so we can multiply. So what I'm going to do here is first I'm going to break this apart to remind myself that when I see something like 5y squared, I have 5 times y squared, right? That's what that is. And then I'm also going to do that with the other one. I have negative 3 times y to the 4th. And then the commutative property says I can switch that any way up because everything is being multiplied, right? It's not being added and then multiplied. It's not being divided or subtracted. Since it's all multiplication, I can switch that up any way I want. So what I'm going to do is I'm going to keep the 5 where it is, but I'm going to move the y squared over, and I'm going to move the negative 3 over, but keep the y to the 4th. So I put all of the numbers first, and then all the variables at the end, just for kind of like purposes, right? Now numbers I can just go ahead and multiply. These are not the same base, right? 5 and negative 3 are not the same base, so I wouldn't add them. I would multiply them. I end up getting negative 15. But then since I have 2 of the same base for y, and I'm sorry, that's not a 21, it's a y to the 4th. Y to the 4th. Since I have the same base of y, I can add those exponents and get y to the 6th. And I have combined my two terms, multiplied them together. Right. So you can do it with numbers. You can use product rule with variables, and you can use product rule with terms. You can just rearrange it, and then all the same things apply. Alrighty, we're going to go on to zero exponent rule now. So if you have any questions about product rule, it's probably the most powerful rule, but you'll see it most often. Definitely want to make sure you got this one down. If you have any questions at all, you need to stop the video and ask now. Alrighty, hope you got your questions answered. Let's jump on down to the zero exponent rule. Use the zero exponent rule to simplify the expression. This one is super, super simple if you remember it. Anything to the 0 power equals what? Let's write that down. Anything to the 0 power is, fill in the blank for me. Anything to the 0 power is what? Somebody raise your hand and tell this up. Okay. The usual three options are 0, 1, or undefined. If you didn't know which one, hopefully you do by now. It is not 0. That is the most common mistake. Nope. It is not undefined. It is 1. Anything to the 0 power is 1. Why? Because we say so. There's an extensive proof about why. Mostly it comes down to the fact that we need it to for everything else to make sense. And so anything to the 0 power is 1. That being known, let's take a look at this. What's 6 to the 0 power? It's not a trick question. That's right, it's 1. 1, that's it. It's not 6. It doesn't change to 6 to the first, right? That's different. I'm not changing the power. Anything to the 0 power becomes 1. So 6 to the 0 is 1. 2 to the 0 is 1. 900 to the 0 is 1. X to the 0 is 1. Everything to the 0 power is going to be 1. That's why we said anything. Alrighty. Let's take a look at B though. We're going to be super, super cautious here because it says negative 6 to the 0. But the question is, do we include that negative or not? Now 6 to the 0 we already saw. That's 1, right? But what's really being asked here? Are we being asked to take negative 6 and raise it to the 0 power? Or are we being asked to take 6 to the 0 power and make it negative? It's actually the second one. We are not trying to say take negative 6 to the 0 power. If we were, we would have written it like this. Negative 6 to the 0 power would be 1. Okay? But notice, what did I add here that was not in the original problem? The parentheses, right? If there are parentheses, then you apply it. That comes back a lot to the distribution rule later, so watch out for that. The parentheses need to be there for that to be negative 1. In this case, what I'm saying is negative of 6 to the 0 power, which would be the negative of 1 or negative 1. We're looking in this problem at a negative 1. So watch out where those parentheses are. If there are no parentheses at all, you are talking about the second case here. So this is actually B. Okay? Very, very different answer, especially when you're working with ginormous things. Like later on, you'll see we have this kind of thing going on. Definitely don't want the difference between a negative 1 and a 1. That could be an entirely different problem. Okay? So watch out for those parentheses. They are very, very important. If they are not there, then the exponent only applies to the thing directly in front of it, not including negatives. Negatives do not automatically get attached to numbers. Let's take a look at one more. We've got 5 to the 0 plus 12 to the 0. This one is a little two-step problem here. Let's tackle it one at a time. What's 5 to the 0, class? That's right, it's 1. What's 12 to the 0? That's right, it's also 1. So if we add those together, we get 2, right? So you can eliminate entire things pretty much down to 1 by just sticking them to the 0 power. So that could have been 5 to the 0, it could have been 100 to the 0, it could have been negative 3,492,000 to the 0, and it would have still been whittled down, in a sense, to the number 1. And that's all you have. Alright, that's the zero exponent rule. Any questions about that, feel free to stop the video before we go on to the negative exponent rule. Alrighty, negative exponent rule. This one is another one of those rules that works because we say so. It's a definition. Okay, so negative exponents, they mean something. They mean to do this. It's not being multiplied negative times. That doesn't make any sense, right? So the negative exponents have a different definition than regular positive exponents. Regular positive exponents means I'm multiplying 0 times, right? Here, A negative exponent actually means use the reciprocal. So we're going to write this down here in this little spot. Use the reciprocal and make the power positive. Make power positive. Okay, so that's kind of how you use the negative exponent rule. You're going to take the reciprocal and make the power positive. So let's look at this first one, 2 to the negative third. Well, what would be the reciprocal of 2 to the negative third? Or in other words, let's do one easier. What's the reciprocal of 2? What's the reciprocal of 2? Who remembers? It's not negative 2. You're thinking of opposite. The reciprocal is the fraction. So that would become 1 over 2. That would be the reciprocal, right? Because 2 would be 2 over 1, and then you flip it over. The reciprocal would be 1/2. Same thing goes here. We're going to take what we see. Let's do it in a different color. We're going to take what we see, and we're going to flip it over a fraction. So we're going to do, instead of 2 to the negative third, it's going to be 1 over 2, and then we're going to use the positive power. So it's 2 to the positive third. So when you flip it, that's what the negative part does. You can think of this as 2 to the negative, or it's the negative version of 2 to the third in a sense, and then you use it to flip it over, but the 3 still remains a 3, so you get a positive 2 to the third. We can simplify that down a little bit. 1 is just 1, so it stays 1. 2 to the third is 2 times 2, which is 4, times 2 again is 1/8. So 2 to the negative third simplifies down to 1/8. All right. We're going to kind of look at B and C together because they're so very, very similar. We have 5z to the negative third and 5z to the negative third. But there is something different. There's one thing different about these. Do you see what it is? Right, it's that negative situation again. It's the same situation as we had up in B of the last problem. So let's take a look at these because it's going to change our answer. In this first one, it is saying 5z, all of it to the negative third. So when we apply this rule, we're going to apply it to all of 5z, right? So the whole thing. So that means I'm going to take this whole thing and I'm going to use the reciprocal. 1 over 5z to the third. So notice the 5 and the z both went to the bottom. Then we can simplify it a little bit. We're going to use something we call the distribution rule, which we will talk about again in just a moment. But basically it says everybody gets 3. So 1 over 5 to the third, z to the third, because they were both in parentheses. And then we can simplify that just a little bit more. We get 1 over 125z to the third. And I'm going to write that just a little bit better because it's very squishy. Okay. Oh, not what I wanted. Okay, so 1 over 125z to the third. That would be our final answer. So the main point here is that the whole thing went down to the bottom, right? Because the whole thing was in parentheses. Pardon me. All right, now let's compare that to C over here, where the whole thing is not in parentheses. The whole thing is not in parentheses. We've got 5z to the negative third. Now if I rewrite this just a teeny bit, it'd be 5 times z to the negative third, right? No parentheses means that negative third is only touching the z. It is not touching the 5. It's an equal sign. So the 5 is just going to chill and remain the same. But what's going to happen to that z to the negative third? Well, we're going to use the negative exponent rule, right? So we're going to take z and make it a reciprocal, just like we did in the first one, just like we did over here in the very first one, in B. But this time it's just the z part. So we're going to have 1 over z to the third. And then we can combine those two back together. We get 5 over z to the third as our final answer. And that is very, very different than the problem we got up here, right? 1 over 125, 125th, that's teeny, 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 right? 125th, that means I have 125 pieces and I only want one of them. Whereas 5 whole pies, that's quite different. Somebody asked you if you want 1/25th of a pie, that's different than 5 whole pies, right? So notice those parentheses played a really big role here. That's quite a different number we just got for these two. All right, D and E are very, very similar, so I'm going to let you guys tackle that now. So go ahead and give those two a try, both of them, D and E, and see if you can distinguish how these are going to change. Okay? How these are going to be different, I should say. So pause the video if you need to, so you can give everybody time to try it out. Remember, if you don't try it out, your homework's going to be way hard. And I don't want your homework to be hard, so. Okay, I hope you paused the video and had time to try these out, but if you didn't, that's your loss. Let's give it a try together. So, negative m to the negative second. Well, again, that negative, not a part of this m to the negative second, right? So this is essentially the case we're going for. That changes into 1, negatives on the outside, over m to the second. So that would be the first one. The negative one, the negative's kind of on the outside, so a negative 1 over m to the second. In the other case, we have negative m to the negative second, so the whole thing goes to the bottom, 1 over negative m to the second. And since anything squared is going to be positive, even negative numbers, then this is going to be a positive m to the second. So we get a negative version versus a positive version, just depending on the parentheses. Alrighty, hopefully that wasn't too complicated. Hopefully you talked about the difference between the two, or you at least got these. If you didn't, then make sure you call people over, call the sub over, get your questions answered, right? Get your questions answered. Okay, I'm going to try and sneak this in here. Not in pink, because we just did that one before. Let's do purple. I'm actually going to erase this real fast. Keep it on your paper. If you need to move it down or something, you can. But I am writing in such a large blocky letters, you hopefully have some room. Okay. So now I have 3 to the negative first plus 4 to the negative first. Up until now we've had just, singletons, but just like in the last problem, it just becomes a 2-step problem. We'll go one at a time. So what is 3 to the negative first? Well, by definition, that means 1 over 3 to the positive first, or 1/3. Same thing goes for 4 to the negative first, right? By definition, that means use the reciprocal, make the power positive. 1 over 4 to the first, or 1 over 4, right? So that's how we would use the negative exponent rule to switch those. Works with numbers, works with variables. Now we can remind ourselves how to add fractions, right? Simplify a little bit. I can't add these as they are. I can't add a 1/3 and a 1/4, right? Try to take those measuring cups, put them together. That's insane. Instead, let's put them in a common measuring cup, right? So a common size. So I'm going to need it over something they have in common. I'll put them over 12, right? So instead of 3, I'll do 12. In order to get a 3 to a 12, I got to have 4 of them. So 1/3 is the same thing as 4/12. And then I'll do the same thing over here. In order to get a 4 to a 12, I need to times it by 3, or in other words, a 1/4 is the same thing as 3/12. Now that they have the same base, I have 4/12 and 3/12. I have 7/12. So that is equal to 7 over 12. There's our answer, 7/12. Nice. Alrighty, that was mostly a review on adding fractions. Just find LCD and then combine the tops, right? Combine the tops. Alright, one last thing with the negative exponent rule. It works in reverse. Works in reverse as well. Remember, I said use the reciprocal. Never did I say make it a fraction, right? Never did I say put it over 1, right? I said use the reciprocal. So if it's already 1 over something, like we have here, my screen went away, sorry about that, like we have here, then it's the same process, right? You just use the reciprocal. Well, the reciprocal of 1/2 is a positive 2. So we just go back, right? In this case, therefore, same thing applies. If I have 1 over 2 to the negative third, I use the reciprocal, 2 over 1 to the positive third, or just 2 to the third, or 8. So in this case, it ended up being a whole number, right? It ended up going from a fraction to a whole number instead of a whole number to a fraction. Alrighty, that is the negative exponent rule, where by definition it means you use the reciprocal and change the power to a positive. If you have any questions about that, you need to stop the video now and get them answered. We got 2 more rules. Well, 3 technically, but 2 more spots. Alright. Next one we're going to talk about is the quotient, and it goes right along the lines of the product rule. Remember, quotient is the opposite of product, so it's division. Division rule, essentially. Don't call it the division rule because it's not really what we're doing. It's more like a canceling rule, but it's called the quotient rule because it deals with the division of 2 things. However, it's got the same setup as the product rule. They have to have the same base. They must have the same base. Must have the same base. I'll say it one more time, must have the same base, or this doesn't work. You're going to see why. Just like in the product rule, we had to have the same base so that they would all combine together. Here we're going to have the same base because we want them to cancel. So there's two ways to think about this. The first one is a break. So the first one is you can subtract them, and we'll come back to that one in just a sec. But the second one is a breakdown and canceling. So here I've got 2 to the third. Oops, I guess I wanted to use red. Just kidding. I've got 3 to the 7th, pardon me, 3 to the 7th over 3 squared, right? That's what I've got. But let's remind ourselves, what does 3 to the 7th actually mean? Well, that means 3 times itself 7 times. So there's 3 of them, 4, 5, 6, 7. And then that is over 3 times 3, right? That's what 3 squared means. If I look at this like that, then how many of these are going to cancel? Remember that anything over itself is equal to 1. And if that is the case, then anything over itself is going to cancel out to 1. So in other words, this part right here is going to cancel to 1, and this part right here is going to cancel to 1. It's going to go away. So how many 3's am I left with? Well, I'm left with 1, 2, 3, 4, 5 on the top, and none on the bottom, so just a 1 on the bottom, and I end up getting 3 to the 5th. Alrighty, sounds good, right? And so it's basically a game of how many can you cancel. If I've got 7 on the top and 2 on the bottom, I can cancel 2 of them. Now, again, another way to think about this is subtraction. You can take the 3 to the 7th minus 2, and that would again give you 3 to the 5th. Just like you can take the shortcut with adding the exponents. Now in this case, sometimes you actually do want to think about it as a canceling. I find some people really like that way better, because when you get with the big stuff like this, it's easier to just cancel the top and the bottom instead of subtracting. But if you've just got nice little expressions like this, then you can remember you can just subtract them. 7 minus 2. You always subtract numerator from denominator, even if it's negative, even if it will be a negative number, okay? Always top from bottom, always numerator from denominator. Let's try it again with B. This time we got variables, but remember again, that just means numbers we don't know, so they're not really that special. I've got 6 p's on the top. That's right, because that gives me p to the 6th over p squared is 2 p's on the bottom. I've got, let's see, 1, 2 that are going to cancel. I'm left with 4 p's on the top, or p to the 4th. Whoop. Sorry about that. Let's write it a little better. Okay, so or I'm left with 4 p's on the top, which is p to the 4th. Now if you don't like that way, you can take p to the 6th minus 2, which would again give you p to the 4th. Same thing. Alright, so that one, even if it's a variable, same exact thing, same exact process. How many from the top and the bottom can you cancel out to 1? And then your answer is how many is left over. Let's try it one more time. K to the 7th over k to the 12th. Well, if we think about that, we've got k, 3, 4, 5, 6, 7 over, oops, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, put 2 over here, 11, and 12. So I've got 7 over 12, right? I've got, these ones are going to cancel. 1, 2, 3, 4, 5, 6, 7. All right. So I've canceled that, right? I've canceled 7 of them. Now, not always are they all going to cancel, right? If it's different, then, or if it's different bases, this doesn't work, but sometimes they're going to cancel. However, what's different in this problem? Why did this one end up slightly different? Hope you see something in the bottom there. They end up on the bottom, right? They end up in the denominator. The k's left over do not end up in the numerator. So this isn't going to be k to the 5th, right? Instead, this is going to be 1 over k to the 5th. 1 over k to the 5th, right? Because that's where my k's lie. The k's are in the denominator. I want to keep them in the denominator. So if the p's are in the numerator, great, keep them in the numerator. If the k's end up being in the denominator, okay, keep them in the denominator, right? And if you have nothing in the numerator, just throw a 1 over it. 1 over k to the 5th. Right, remember you can always tack on a plus 1, or times 1. Again, we can think about this as subtraction as well. Always subtract the numerator minus the denominator, right? So 7 minus 12 gives us k to the negative fifth. And then we just saw in the negative exponent rule, that means 1 over k to the fifth. So we get the same thing. Alrighty. That is the quotient rule. Quotient rule, pretty cool. Any questions at all, pause the video now and talk about it. Alright, one more rule. There are two more rules technically, but one more section today, and before we tackle this big guy. The power rules. Now there's actually two of them. There's power of a power, if we go back up to our chart here. There's power of a power, which we'll talk about first. And then there's distribution, and they're so very, very similar to each other that we've roped them into one section. But notice they both involve parentheses, so don't mix them up, okay? Don't mix them up. There's power of a power and distribution. So let's talk about power of a power first. Here we are. Power of a power looks like this. So you've got one base this time. This looks kind of similar to product rule, right, where you've got multiple exponents on the same base going on here. But notice that it's only one power. It's only one base. P to excuse me. Got some dust in my throat. P to the 8th to the 3rd, right? There's a lot of to thas. It's not times anything. It's not divided. It's no negatives. Nothing like that. But it's power to the power, right? So P to the 8th to the 3rd. Now, if we think about this as just considering P to the 8th, right, we'll consider that an entity, and we're going to times it by itself 3 times. So we're going to do the outside one first. So P to the 8th to the 3rd means P to the 8th times P to the 8th times P to the 8th, right? In other words, I have 3 P to the 8ths I need to multiply. Now I can use the product rule. If I use the product rule, then I have P to the 8 plus 8 plus 8, right? Or P to the 24th. And that's how I'd simplify that bad boy up. But if we look at this a little slightly differently, no matter how many times that second exponent is, those are always going to be P to the 8ths, right? Because that's what it means. That's what the exponent means there. It means take the same thing and multiply by itself 3 times. So another way to think about this would be P to the 8th times 3 instead of plus 8 plus 8 plus 8 plus 8 plus 8. So in other words, we do P to the 8th times 3 and we get P to the 24th. The same thing. So you can think about it in multiples, or you can think about it in multiplication, right? Because that's what a multiple is, right? If you've got multiple 8s going on, then just multiply how many 8s you have, right? Use your standard, your basic algebra rules that you remember. So the power of a power rule says if you have one base being raised first to one power and then to another, then you can multiply those powers and you get those exponents and you get a simplified P to the 24th. And that would be our final answer. Alrighty. That's the power of a power rule. Sometimes it's roped in with the distribution rule. So let's talk about the distribution rule now. But if you have any questions at all, pause on the power of power rule. Okay, we'll go over here to the distribution rule. Distribution rule comes in 2 forms. You can see it when you're dealing with quotients, with fractions, or you can see it when you're dealing with multiplication. So we're actually going to start here because we've seen this once today already. So go ahead and jump over to C. We'll come back to B in like 30 seconds. But jump over to C. We have 3m to the 5th. My first question for you is, does that 5th apply to the 3? Does it apply to the 3? Talk about it if you don't remember. It does apply to the 3. Hopefully you had time to talk about that. It applies to the 3 because the 3 is in parentheses, right? The 3 is in the parentheses. It's telling the audience, yes, take all of this stuff inside this parentheses and raise it to the 5th. It's not saying 3 times m to the 5th. It's saying 3m to the 5th, right? All of it together. So the distribution rule says you can simplify this a little bit by distributing. That's exactly why we call it the distribution rule. So we'll distribute, I don't want to write it. Oh, right, it's fine. Distribute that 5 to both of those, okay? So in other words, what we have is 3 to the 5th, m to the 5th. If we did want to split them up, right, if we wanted to give them each their own little case, then we would say that, yes, this applies to both the first one and the second one. In other words, I can write a 5 on the first one and the second one. So I can write it like that. And then when we do that, 3 to the 5th Well, 3 times 3 would be 9. Times 3 again would be 27. Times 3 again would be 81. Times 3 one more time would be 243. And then since we don't know m, we can't exactly compute it out. Oh, darn it. Or in other words, we get 243 m to the 5th. 243 m to the 5th. Very different than 3m to the 5th, right? If you had 3 friends versus 243 friends on Facebook or Instagram, that's a little more popular, right? So we want to make sure we get those powers in. It also works with fractions as well. So if you've got multiple things, basically the distribution rule says if you've got multiple things to 1 power, you distribute. So if that comes in the form of multiplication, great, product rule. Or for us, comes in the form of a product, not product rule, then great. If you've got something in the form of a quotient, like a fraction, 2 over 3, it's the same idea. You just multiply in that 4, or distribute in that 4 to both of them. So in other words, here I've got 2 to the 4th over 3 to the 4th. Now I don't multiply base times exponent. Never once have I done that, right? It's not what it means. This is not going to be 8 over 12. It's 2 to the 4th over 3 to the 4th. In other words, 2 times 2 times 2 times 2 over 3 times 3 times 3 times 3. Or 16 over 81. Cool. So just distribute. That's really what the distribution rule says. All right, any questions at all? Pause. Get your questions answered about the distribution rule. The next problem we're going to do, actually, after you've answered those questions, go ahead and tackle the next problem. This involves both of them, both the power of a power and the distribution rule, which is often how you'll see it. So go ahead and try using both of those on this one problem here to simplify as far as you can. Okay, hope you had some time to pause the video and talk about it. Let's start here. So I've got all of this, negative 2m to the 5th over z, all of it to the 3rd power. I'm going to start with that distribution rule because it seems a little bit easier. So I'm going to start with the distribution rule. And when I do that, the negative's just going to still chill on the outside. And I have 2 to the 3rd, m to the 5th to the 3rd, all over z to the 3rd. If you forgot the 2 to the 3rd part, know that you made a common mistake. That happens a lot. Even if it's a coefficient, right? Just like we saw, everything in the parentheses gets the exponent. So make sure you actually put the 3 on the 2 as well. Now I can simplify some things. I've got a power to the power rule here that I can use. M to the 5th to the 3rd is going to be m to the 15th, right? So multiply those. Power of a power says if I have if I have 2 raisings, 2 powers, right, 2 exponents, then I multiply them together. So I have m to the 15th, 5 times 3. Those other ones I can just, the coefficient I can just simplify. 2 to the 3rd would be 8, right, and that negative's on the outside, so I don't have to worry about that. And then z to the 3rd is as simplified as it's going to be. So our final answer, negative 8m to the 15th over z to the 3rd. There we are. Alrighty. Now, okay, so that's all of our exponent rules. That's all of our exponent rules. We have power rules, we have power of power, distribution, quotient rule, negative exponent rule, zero exponent rule, and product rule. Right, so we got 6 of them. You are responsible for knowing them all, right? But a lot of these you can see are just combining stuff. You can just think about what does it mean to be an exponent. And when you remember that, a lot of this stuff just falls out of it, right? So you don't need to worry, what did the quotient rule say? No, just think, okay, I've got p's on the top, p is on the bottom. They cancel. Great, moving on with life, right? These are all going to come in handy when you see big stuff like this. Like I've been kind of hinting at that this entire video. This is probably what you'll see on a test. We will probably not give you teeny tiny things like this. I say probably because you never know, but it'll probably be big stuff like this where you have to use all 6 rules at the same time. Okay, so let's read the directions because that's always important. Example 1.6. Use any of the above rules to simplify this expression so there are no negative exponents and only one of each base. That's how you know you're finished. You have no negative exponents and only one of each base. So a lot of the time people think, well, I simplified this part, am I done? Am I done? All you need to check is that none of your exponents are negative, and you only have one of each base. So if you had x, y, z, you better only have one x, one y, one z. And look at that, that seems to be the case here. So let's try this out. Luckily, with our exponent rules, you can do them in any order you want. There is always the fastest way, but since it varies from problem to problem, you can do that in any order you want, okay? Any order. I like to kind of follow PEMDAS when I'm doing this, so I'm going to start in the parentheses, because that way I can avoid big numbers. If you want to start with distribution rule and distribute that 2 out to everybody, go for it. But I'm going to do it in the parentheses. So I'm going to start over here. Alright, I think I'm going to start by getting rid of the 0. So anything to the 0 power is what? Anything to the 0 power is 1. That's right. So since these are to the 0 power and they just equal 1, that's going to be like all of this stuff times 1. In other words, they go away. So I've got left over, big old parentheses, fraction, negative y to the 6th, z to the 7th. And I really should put a pause when I say that, right? Negative times y to the 6th, because that's not in parentheses, right? There isn't a negative y being raised to the 6th. It's negative version of y to the 6th. That'll be important later. X to the 4th, y to the negative 2. On the bottom, I have x to the 9th, z to the 4th, and x squared. X to the 9th, z to the 4th, and x squared. I'll just double check that. And it's still all being raised to the 2nd power. So that's what's left over from here. Choose a different color. Alright, cool. Whittled it down a little bit, but I still see negative exponents and I still see multiple of the same base, so I'm not quite done. So now I think I'm going to take care of negative exponents. I think anything with a negative exponent on it, I'm going to take to the bottom. I'm going to use the negative exponent rule. Now I got to be careful. This thing right here, that's not a negative exponent. That's a negative 1, right? That's a coefficient, right? That's a number on the side. What I'm looking for are things like this. Negative powers, negative exponents. So remember, it's important to know when you're talking about a base or an exponent. We've been using those words a lot today. If you think the negative exponent rule applies to anything that looks like a negative, you're going to have a hard time. You got to remember, it's a negative exponent that I'm looking for. So it looks like the only thing that's going to happen is this y to the negative 2nd. And I'm going to take that and use the reciprocal, which is 1 over y to the 2nd, or in other words, it's going to go to the bottom. Everybody else is going to stay the same. So again, a big old parentheses, it's still squared. I still have a negative out front. Y to the 6th, z to the 7th, x to the 4th. Now the y squared is going to be on the bottom, but I'll get that in a sec. X to the 9th, z to the 4th, x squared, y squared. So the only thing that changed is that y squared went on the bottom. Alright, cool, I got half my stuff done. No more negative exponents. Sweet. Hopefully I can get down to a single of each base, right? And no more parentheses. Alright, I think I'm going to go over here now. Do it in blue. Let's see. What can I get rid of now? I think the next step I'm going to take is the product rule. I think I'm going to see if I have anything on the same level that I can multiply together. So remember, that's what's happening here. These are all multiplication. Well, product rule says it has to be the same base, so it's got to be the same letter, right? It's got to be the same letter. I don't have any of the same letter on the top, but on the bottom I have a couple x's. I have a couple x's. Commutative property says I can switch it into any order I want, so I can combine this guy and this guy. I think I'm going to go ahead and do that. Everything else stays the same. Still got a squared. On the top I still have a negative y to the 6th, z to the 7th, x to the 4th. But now on the bottom, my x's, let's see, I've got 9 of them and 2 more. 9 plus 2 is 11, so I've got x to the 11th. And then the other 2 are z and a y, so they just stay the same. Z to the 4th, y squared. And that's still all being squared. Cool. Getting there. I'm getting there. I've still got some multiples of each base, though. So, luckily, I've now got one of each on the top and one of each on the bottom. So I got rid of that, right? No doubles within the same level. But I think I'm going to use quotient rules to get rid of the doubles altogether. So this time, let's use quotient rules. So anything on the top will cancel with anything on the bottom as long as they're the same base. So let's start with the y's. Looks like I've got 6 y's on top, 2 on the bottom. Means I'm going to cancel, let's see, 6 on the top, get rid of the 2 that cancel with the bottom. That leaves me 4 on the top. Actually, you know what? I'm going to put this up top so that we have room for one more if we need it. I'm going to erase that. Then, oops. Gotta go get my pen back. Alright. Now, so I'm going to put this up here. So we just talked about how I have y to the 6th and y squared. That leaves me with y to the 4th. I still have that negative out front, so it's just going to sit out front. Let's see, let's do the same thing with the z's. I have 7 on the top and 4 on the bottom. Looks like that's going to leave me with 3 on the top. So z to the 3rd on the top, right? I got no more on the bottom because I canceled all the bottom. And then the x's. Now this one's a little different, right? Just a little bit though, because I've got more on the bottom than I do on the top. So when I cancel 11 and 4, subtract those, 4 minus 11 would be negative 7, right? In other words, I've got 7 on the bottom. So you see what I mean by sometimes the canceling way is a little more convenient, right? But it's the same logic, right? If I cancel them, I would get, or if I subtracted them, I get negative 7. That's a reciprocal, would be 1 over positive 7. 1 over x to the positive 7, so that's usually where it ends up. But this is kind of a more structural way to think about it, in my sense. And then that's still all being raised to the 2nd. Alright, cool. So I've got no negative exponents. I have 1 of each base. Fabulous. One more step, though. I really don't like that 2 on the outside. So we're going to use the distribution rule just to make our life a little easier. And we're going to do everything squared. So everything is now to the 2nd power. That's the 2nd power. That's the 2nd power. That's the 2nd power. And even that is to the 2nd power. That negative 1 is to the 2nd power. So this ends up being a positive, right? Negative 1 times negative 1 is going to be a positive 1, so that negative actually goes away. And now we've got y to the 4th squared. So y to the 4th to the 2nd is going to be y to the 4 times 2, or y to the 8th. Same thing over here. We multiply 3 and 2 to get z to the 6th. And on the bottom, multiply 7 times 2, or x to the 14th. And now I don't even need the parentheses because there's nothing on the outside anymore. So I just end up with this as my final answer. Notice I've got all positive exponents, right? Positive exponents. And 1x, 1y, 1z, 1 of each base. And that's so much simpler. I could write it so much bigger than I could the original problem because there weren't so many multiples going on. So it's much easier to see something like this than it would be something like that. And that's how we combine exponents. Alright, we've talked about a lot of stuff today. We've talked about 6 different rules for combining exponents. Your homework tonight is the exponent rules worksheet, right? Your homework tonight's going to be that. Consult Canvas for exactly what to do on that. In just a sec, you can, Mr. Walsh is going to write it on the board. And if you have any questions at all, remember, you've got so many outlets to work with. You've got the sub. You've got other teachers in the math department you can come talk to. You can check out this video again on Canvas at home. You can come into after-school tutoring, right? We have laptops and you're welcome to look at videos. You can come in to get help, and any of the 4 math teachers that will be working in the after-school tutoring. You can see Ms. Waters' first schedule. You can come in at engagement time. You can come in at advisory, right? You've got tools to work with here. Please, please, please do not just sit there and think, oh, Miss K's out, I don't have to do any math homework, because that is not the case, okay? That's not the case. You need to get this stuff done. Next time we will be continuing right where we left off. So if you have any questions, go ahead and get them answered. Otherwise, you may begin your homework now.